from two topological spaces. So suppose you have two topological spaces x and y, and given a map f from x to y, then there be a map. Then the set, which will be denoted by g suffix f, or sometimes it is denoted by graph f. Okay. So then the set denoted by this, consisting of the ordered pair x f of x, where x belongs to capital X, is called the graph of the function. It's called the graph of the given map f. So this is called the graph of the map this. That means GF is a, so GF is a subset of x cross y. Okay. So x cross y is the product space. So GF is a subspace in this product space x cross y. Okay. Now suppose you have, now note that, now if f is continuous, if okay, let us suppose that suppose you take to note that if you take xy to be nonlinear spaces, okay, and the map f from x to y be continuous, or you may equivalently take it as bounded. So this is continuous, then the graph must be closed. It is a closed set in the product space x cross y. Why? Because if you take nonlinear spaces, then suppose you take an ordered pair belongs to the closure of this graph, then what will happen? So being nonlinear spaces, so there exists a sequence xn in x such that you can form a sequence xn fxn in GF such that this is a subset of GF which converges to xy. Okay, since it is in the closure of this set, so you can find out one sequence in x which will give you the sequence in GF that converges to xy. So since this sequence converges to xy, so this implies, so if you take the norm of xn fxn minus xy, so that should be tend to 0 as you take it to infinity, and this implies, so since you are in the product space, so in the so the norm in x cross y is something like that. So it is norm of xn minus x plus norm of fxn minus y. So that will be, so that So that is so this tends to 0 as n tends to infinity, and this implies, so since these are two non-negative reals,
স্যার দেখুন না একটু কৃষ্ণ মনে হয়
হ্যাঁ
আর্টস জয়েন করেছে
হ্যাঁ ও আচ্ছা 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 আচ্ছা
কৃষ্ণ মনে হয় স্যার
এক মিনিট হুম, 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 হুম। কই আবার বলো করতে
ঠিক আছে স্যার বলছি
okay. So since these are two non-negative reals and their sum is tending to 0 as n tends to infinity, so will be there, so the respective norms will be tending to 0. Okay, as n tends to infinity. So that means xn tends to x in capital X and fxn tends to y as n tends to infinity. Okay, but you have assumed that, but f is continuous, right? And due to continuity, so it will preserve the sequential convergence. So therefore, since xn tends to x, so fxn will be tending to x fx as n tends to infinity. But you have already proved that fxn tends to y. So since you are living in the nonlinear spaces, so it is a metric space, that means it is a Hausdorff. So the limit of this sequence must be unique. So therefore, this limit y and fx, they will be same. So y equal to fx. So that means the point xy looks like x fx. So therefore, it is in the graph of the map. So this proves that. So this proves that GF bar coincides with GF, that is GF is closed. So therefore, if you consider a continuous map from a nonlinear space to another nonlinear space A y, so then the graph must be a closed set. Now if you take the converse of this observation, okay, so what about the converse? What about the converse? The answer is no. The converse is not true in general, because if you take, suppose let us consider X to be the space of all functions, continuous maps in the closed interval 0 1, such that which are differentiable. So if dash exists and the derivative is also continuous. Okay, so you are taking those continuous functions which are differentiable and whose derivative is also continuous, and you take y as the set of all space of all continuous real valued continuous functions from on the closed interval 0 1. So if you look at these spaces, so you will see that this x is a subset of y. Okay. Now, so with respect to, so these are two nonlinear spaces. So with respect to, so we induce the subnorm on C01, and since it is a subset of y, so you can induce the same norm over x also. So x and y are two nonlinear spaces, and now you define a map T from x to y by the rule. So Tf goes to f dash, and that is f goes to its derivative. Okay, fine. Now let us define, so let us define a sequence of functions fn t is equal to t to the power n. Okay, then these fn's are continuous maps. Not only that, these are differentiable, and in addition to this, the derivative function is also continuous. So fn's are in x. Now if you take the norm of fn, then what is the norm? The norm is sup of mod fn t, where t belongs to the closed interval 0 1. So this implies sup of mod t to the power n, t belongs to the closed interval 0 1. So therefore the supremum will be 1, right? So norm fn is 1. Now, so this implies, so now what is now, so you take norm of t fn, sorry, norm of t fn t. Okay. Now what is t fn? Now since tf is f dashed, so that means tft, that is tf of t, it is f dash t. Okay. Now what is your fn? Fn is t to the power n. So what is fn dashed? So n t to the power n minus 1. So therefore it is norm of n t to the power n minus 1. Okay. So that means it is n mod of t to the power n minus 1. Now since t belongs to the closed interval 0 1, so using this you will have, so this will be less or equal to n. So this implies, so norm of t fn must be less or equal to n. Okay. Now since, what is t fn of 1? So this is n, right? So at some point it assumes the value n. So therefore the norm must be equal to n. So norm of t fn is n. So hence, so therefore the norm of t must be, so sup of norm of t fn by norm of fn, where f this one. Okay, this. So what is that? So therefore, so norm of t fn is n, and norm of fn has been deduced as 1. So therefore it is actually n, sup of n, right? It is actually sup of n. So therefore what is sup of n? So this sequence diverges. So therefore it is plus infinity. So this implies t will not be bounded. T is not bounded, and since it is not bounded, so which means that T is not continuous. So the map that has been defined above is not a continuous map, but you still have the property that the graph of this function is closed. Okay, so although the graph of the function is closed, but still the function will not going to be continuous. So how can you show that the graph is a closed set in the product space?